So just a quick introduction to myself. Thank you for the introduction, Pete. I've been working with databases for a couple of decades, first as a developer, and after a few years of developing software and then discovering that I loved databases more, I started writing on my blog about pretty much everything that I was learning about, and that got me the opportunity to co-author this book, and then I joined the co-authors of that book in their company, Percona. So I was a database consultant for 4 or 5 years, something like that, through the fast growth period of MySQL and Web 2.0. And so I got to consult alongside a bunch of really interesting customers who were pushing what MySQL could do. A lot of that was around the internal limitations of MySQL, in particular, some of it, the internal code of the database rather than the code that people were running in the database. And that led me to understand a performance-based mindset. And after a while, I started writing tools around that. Most of it is open source, so it's the Percona toolkit. It's InnoTop, it's Percona monitoring plugins now. So this is all open source software that I wrote, some of which is still widely used today. But after a while, I realized this could be turned into a product, or these ideas could be turned into a product. So I left Percona and founded a company called VividCortex, and we do database performance monitoring, essentially for some of the similar kinds of use cases. If you have large-scale MySQL, Postgres, MongoDB, Redis, and you don't measure it, which I can say with probably 99% certainty you don't measure what it's doing, then we are a great way to measure that at any scale with essentially zero performance overhead. So that's kind of my background and where we are today. The company's 5 or 6 years old. I've stepped down as CEO recently, hired a new CEO, and now I'm CTO, so I get to focus a lot more on the technology and spend a lot more time in product with customers, which is great. These slides are going to be online. I've got an introduction slide here I'm going to skip past because that's for people who are viewing the slides online. So what are we going to talk about today? This is about quantifying system scalability, and it's much simpler than it sounds if you understand how to sort of approach it in a productive way. We'll start with a typical way that a lot of people do this, which is through the science of computer performance as the utilization and response time are related to each other. And this is a great place to start because it's where a lot of the existing literature is. And I'll kind of explore that for a little bit, and then we'll pivot over into starting to define what scalability means from a similar kind of mathematical perspective. There's no need for any mathematical knowledge here. What I really want to do is just build intuition through all of these things. After that, we'll extend Amdahl's law into the Universal Scalability Law, which is a relatively recent articulation of the math of how systems scale. And then we'll see how to apply that in the real world using one of our servers that I just grabbed some data from last night as kind of a test data set. And then we'll see what kinds of interesting things we can do with that. And my goal is for you to have some takeaways that you can go home and apply this to your own systems, or maybe even just here this afternoon, because it's quite simple. It's kind of spreadsheet sort of math. That's what we'll talk about today. So let's start with queuing theory. And this is actually the mathiest, nerdiest part of it, because this is about a century-old discipline, and there's a lot of complexity here. It turns out that there's queuing theory is basically probability, and probability is really, really complicated to understand and apply. And so what I'm going to try and do is skim around the things that are the most useful and give you some foundation for maybe going deeper on queuing theory if you want to. But then I'm also going to kind of do a bait and switch at the end and get out of queuing theory. So queuing theory is this branch of operations research. It started with telecommunications capacity planning. And Gene Amdahl was, sorry, it's not Gene Amdahl. And I'm forgetting, Agner Erlang, was trying to answer the question, how many telephone lines do I need to have to give people the ability to place a call with a certain amount of waiting online for a circuit to open up? And what he discovered has turned into this rich set of theory and practice that's useful in all kinds of things, like how many lines do we need open, how many cash registers do we need open at the shopping center so that people don't have to wait too long in line to check out their groceries, things like that. It's all kinds of weighting analysis, and it turns out that probability is a really important part of that, which is what makes it both interesting and hard. So what causes things to wait is basically irregularity of jobs. Jobs arrive at a system and they take some amount of time to be processed, and when they arrive irregularly or when there are too many of them to fit into the available time for processing, then this time gets lost because of overlapping jobs, and this has really counterintuitive kind of explosive behavior. And a queue is what you place in front of a system to make it more available. If you don't have a queue, then if a job arrives at a system and there's another job in process, then it's unavailable and the job has to fail. If it doesn't have some place to wait, then you get max connections exceeded or some kind of similar type of a phenomenon, but the system is not available while another job is running. And this could be a request response in a web server, or a query to a database server, or arriving at the checkout line at the grocery store, whatever it is. Because you wait in the queue, it increases how long you actually wait to get your job done. So queues increase waiting and reduce response or increase response time. And it also increases the cost and overhead of running the system. So if we look at something like a web server, if you have a queue in front of it, or if we look at the networking stack and the operating system, when you have a queue in front of it, it's one more thing that has to be managed. So it's not free to have a queue. But it does increase availability and utilization by time shifting things so that there's more ability for the system to have a job ready to process when it is ready. I'm going to explain it graphically, and I've totally ripped this idea off from Eben Freeman at Honeycomb. He did a phenomenal job of visualizing this and explaining kind of the essence of it. So I'm basically taking this whole section of slides from him. And I've got a link to his slides at the end, and his talk at Lisa is on YouTube, and all that stuff is linked in the resources at the end of the slides. So we have some arrival rate lambda, and we have some job, which is this long in the timeline, and it's this high, it's the same height in the vertical size. So it's kind of a visualization that a job arrives and it's this high, and as time progresses, it gets worn down or used up or completed, and so we get a triangle with a 45-degree slope. And the server is processing it during that time. So the upper edge of that triangle at any moment in time is the amount of work left to do, and when that gets down to 0, then the job is done. What happens when another request arrives and the first one is still in process? Well, we get a red parallelogram, and when the first job is done, then the second one has another gray triangle. And here I'm going to introduce just a little bit of the queuing notation. So R is the residence time, response time, you can also call it latency, but R is the letter that I will use pretty uniformly for this, not only in this presentation, but just that's the letter that I use for this. And R is composed of two things. First, there's S, the service time, so that's the time that it takes for the job to actually run. That's the time that it takes for the cashier to actually do your groceries, for example. And then there's W, the waiting time component. And you add those two together and you get your total time to check out, or you get your total time for the query to execute, or whatever it is. And so that's kind of a really fundamental thing in queuing theory analysis. And if we have multiples of these things, you can see how the queues kind of pile up. Maybe requests even stack on top of each other in the queue. And Eben does this really clever thing where he uses a little bit of math. I'm not going to go through it here, but you can watch his talk and see how it's done, to relate the vertical and horizontal dimensions here and derive this equation. Now, this is an equation that can be derived multiple ways, but this is a really cool, intuitive, visual way to do this. And you solve for W, the wait time, and that is the wait time in the queue. It's not the total response time. And you get this formula, which is related in terms of how long it takes a job to be done and how fast they arrive, which is essentially another way to state how busy the server is going to be processing those jobs. And then I've drawn a picture of what the curve of that looks like. I've translated it into the utilization domain, which is typically how queuing theory is formulated, is response time versus utilization rather than the arrival rate. So I'm just kind of trying to relate that into something that might be a little bit more familiar if you go look at textbooks or whatever. But you get this hockey stick curve. Now, warning, this hockey stick curve's perspective, the aspect ratio is highly skewed. To flatten it out, it's actually much steeper than that. But generally what happens is as utilization increases and gets close to 1, and utilization cannot go higher than 1, fully utilized is as full as the server can get, suddenly the response times spike up dramatically, very dramatically. And that is kind of the fundamental takeaway from queuing theory, or one of the fundamental takeaways from queuing theory, is that as systems get busier, they very non-linearly get much less responsive, and customers have to wait much, much, much longer. The nice thing about this way of formulating the response time or the wait time equation is that you can look at it and kind of intuit some things from it very easily. So just as a thought experiment, if you were to double the arrival rate and halve the service time, then what happens is that the numerator becomes half the size, but the denominator remains the same. And so the queue wait gets cut in half if you shrink the service time. So the queue wait is very sensitive to the service time. Those things are related to each other very, very closely. And that's really important. Other things that are very related to the queue wait time are, as I mentioned a little bit earlier, the variability, how much these things vary in the frequency or the inter-arrival time, therefore how much they're going to overlap, because overlapping is what contributes to that explosion in queue wait. So this is really good for building intuition about how, as you start to push systems to their capacity, suddenly they start kind of pushing back at you, and everybody gets a miserable experience who's a customer of this system. But the hard part is how you actually translate this into practice. How do you go and use this in your systems to figure out, predict performance, understand how much capacity you're going to need? The part of this that's hard is actually turns out to be measuring the service time and the inter-arrival times and understanding the statistical distribution of those things, and therefore which of many queuing models to use for this. What I've shown you is kind of a gross oversimplification, but the intuition is still valid. The application is hard. So great kind of takeaways from that intuition is that any system is going to have some amount of queuing. Literally any system. Queuing starts before the system starts getting very busy at all. Even if it's a small amount of queuing, it is there. And it escalates really suddenly, that escalated fast. And it's very sensitive to the service time and various kinds of variability. And then the thing that I'm going to say that does not follow from anything that I've said is that this causes nonlinear scalability. It is one of two causes of nonlinear scalability. And I'm going to switch now. I said rabbit out of the hat, bait and switch. I'm going to switch into that next, and then I'll introduce the other cause of nonlinear scalability a little bit later. All right, so let's switch into a relationship called Amdahl's law, which is from Jean Amdahl. And it defines essentially how much do things get faster as you parallelize them. There's a couple of ways that you can tilt and rewrite this equation, but that's kind of the gist of it, is how much speed up do you get from parallelizing. So this really starts to define and get at the root of what scalability is. Scalability is a function of concurrency. Remember those triangles stacked on top of each other? When there's one triangle, there's concurrency of 1. When you've got one stacked on top waiting, you've got concurrency of 2. Concurrency is a really fundamental property of a system's workload. It turns out to be kind of the central thing, the hub of the wheel from which all of the spokes radiate in performance theory. One way or another, concurrency is at the root of it. I talked about utilization. Utilization is just concurrency of the server itself. So there's a mathematical definition of scalability that follows from concurrency. Concurrency is also the canonical definition of system load. So we can think of scalability in terms of system load as well. So I'm going to illustrate one of these parallel processing systems where we got some job, And we're going to break it up into smaller jobs. So we've got a long job, and then there's 3 kind of subcomponents. And if we take those and run them in parallel, then the response time should shrink to 1/3 of the original response time, right? And if it's done faster, then we can do more of them. We can get higher throughput. We can get a higher rate of completions over time, right? So we're seeing a function here that throughput is a function of concurrency. And that's kind of where we're going with scalability. Ideal linear scalability is precisely like this picture on the right-hand side here. If we can divide this into 3 equal parts, then we can do 3 times as many of them, right? So with concurrency of 3, we will get 3 times the throughput. So now I'm starting to relate concurrency on the bottom with throughput on the vertical axis. And you're going to see me expand on that a little bit more. These are the 2 fundamental dimensions of scalability. So this relationship is really important. And our ideal scalability is linear. There's lots of marketing talk about linear scalability. When you do the math on it, just take some of the measurements off of a benchmark, plug them into a spreadsheet, and extrapolate out from the first measurement. You will see whether it is linear or not. So it's really easy to figure out whether you've got truly linear scalability or not. All right, so this is linear scalability. And this is our ideal. A lot of times people will think of linear scalability and say something like, you know, linear scalability doesn't imply that the constant of scaling is 1 or some similar kind of a phrase. But beware of that thinking, because if 1 unit of concurrency produces 1 unit of throughput and 2 produces 1 times 2 times a constant of scalability, such as 0.97 or something like that, if you actually follow that train of thought to its logical conclusion, you will see that you do not get linear, you get a curve. And in fact, you will get Amdahl's law curve, which has an asymptote, which I'm going to show you in a few minutes. So don't accept a kind of thinking that is, you know, that there's some kind of sort of constant in there that's less than 1 and it's still linear, because it's not linear. So if we put this into an equation, then we get the slope of gamma, and n is the unit of concurrency. I'll also use that very consistently. That's the number of things running at a time, and it's all over 1. I didn't have to put it over 1, but I'm going to build on this equation a little bit, and you'll see how I'm going to chug some other things into the bottom of that equation. All right, so it's handy to start with the 1. So x is the symbol for throughput. So x at a given n is equal to some constant slope of the line times 1. Divided by 1. But unfortunately, our cluster is never perfect. If we can't subdivide those tasks evenly, or more importantly, if there's a part that can't be subdivided, then we get some serialized portion, maybe at the beginning, maybe at the end, maybe both. So I've notated that with gray here, and you see that now some portion of our process might run 3 times as fast, but overall the whole process is not going to run 3 times as fast. And to express that mathematically, we can add in another component onto the the denominator of our equation with a serialized fraction. And I'm using the Universal Scalability Law's notation of sigma here for this serialized fraction. And that's the stuff that starts to deteriorate scalability. So I've kind of shown what the curve looks like, kind of pulling away from the linear scalability slope up to 3, 4 nodes. So that's what it starts to look like. We start to level off, and eventually that line will approach an asymptote. Serialization is queuing. So this is where I'm going to loop it back into that first section. This serialization, that's exactly what queuing does. Queuing is when access to a resource is restricted and you have to wait in line. That's the definition of serialization. So although these are in a little bit different domains, and it's a little tough to actually make the mathematical link between them, I think that's a career effort for lots of people. At MIT and places like that. We won't go into that here, but you can just trust me that these different domains are actually linked. I mentioned that there's an asymptote. When we kind of take this limit to infinity, what happens if you kind of cancel out and take the limit of infinity? You go to 1 over sigma. Everything else kind of disappears. So another way to say that is if we have 5% serialization, then ultimately, no matter how small we subdivide that thing in the middle, our task can't run faster than 5% of the original total because that's the serialized gray portions at the beginning and the end. And no matter how many servers we use, how much parallelization, we still only get effectively a 20x speed up if we have 5% serialization. So that curve is going to level off at the throughput of 20 times the slope. All right, so that's Amdahl's law, and hopefully you agree with me that this is not going too deep, that we can all, this is kind of still in the realm of intuition. We're going to add one more component on here and see how this turns into a fuller definition of scalability that we can use. So our cluster is not only imperfect in that there's some serialized workload, but most kinds of clustered or parallel processing systems also have some interaction between the tasks. And this is deadly because when one of the threads or processes has to coordinate with another one, ask it for some data, they both stop working on their job and they start working on each other. And what this means is that as we subdivide and increase the concurrency, we're actually adding a significant amount of cost to the overall job of processing our tasks. And so I've notated that by adding in orange, and I've got the original length of these tasks in the dotted lines, and then I've added as much runtime to the end as the orange takes out of the middle because they had to pause. So the service time of these tasks actually increases. This is not queuing because it's extra work that they're doing. They're not waiting idly in a queue, they're actively working and typically making each other work. And this gets really bad really, really fast because the worst case is that each task is asking all of the other tasks to help it do something or to do something for it, and that relationship explodes really fast. The worst case is that there's n times n minus 1 pairs of interactions between these tasks, which grows order n squared. And I'm going to take that n times n minus 1 and put another component in front of it, a fraction in front of it, and put it onto the bottom of Amdahl's law. And so when that happens, I put kappa, that's our coefficient, put kappa in front of n times n minus 1, put it on the bottom of this equation, and we get the first full view of the Universal Scalability Law. So I call this crosstalk. Neil Gunther, who created the Universal Scalability Law, calls it coherence. There's a couple of other terms that'll float around. Coordination penalty. And what happens is that not only does our curve level off, and the aspect ratio of this diagram is a little bit hard to see, but it can actually and will actually go downwards. So we get retrograde scalability. And if you think about this, you've probably seen this a lot in system benchmarks. Many system benchmarks like cluster databases and things like that will have a benchmark where they'll show you the throughput of that system compared to the number of workers or the number of threads or something like that. And the stereotypical thing is that you will have the number of workers in some powers of 2. So you'll have like 1, 2, 4, 8, 16, up to, let's say, 256. So you have to kind of be careful with looking at the horizontal axis of those charts. But what you'll see is usually something that goes up and then starts to slide again. And ideally, it would just keep going up. A lot of vendors are really just trying to stop the degradation and show that their system will flatten off and then not deteriorate in performance past some point. But if you look at those and you kind of translate that logarithmic horizontal axis, you will see a curve that looks very much like the blue curve here. And that nonlinear behavior, that highly nonlinear behavior and the retrograde performance of you ask it to do more work and it stops getting more work done and even gets less work done is explained by that last component that we added to Amdahl's law and made it the Universal Scalability Law. So you can click through, there's an interactive web-based calculator here if you grab the slides a little bit later, and you can drag some sliders around and just see how sensitive this is. The cost of the coordination or crosstalk penalty grows really, really fast as compared to the cost of the serialization or queuing penalty. And so that's like the death knell for any kind of a highly parallel or system that's designed for scalability. So when you've probably been at some conferences or read some papers or something like that where people say, we've designed this system for linear scalability, we made it highly sharded and we can grow it infinitely. Well, you may be able to grow it infinitely, but you will not necessarily get linear scalability. In fact, very few systems are truly linearly scalable. They may be possible to grow. They may not have any fixed capacity limit on them, but what happens is that as you grow them, you will start paying a huge amount of overhead and you get this diminishing return on investment. All right, so let's see how to apply this. This is all the theory. We're not going to do any more theory. Let's see how to apply this in the real world. It turns out to be really, really easy. We can take a couple of metrics. So last night I grabbed some metrics from one of the database servers running in our system, and I grabbed concurrency and throughput. And I have no units. You don't get to see the time scale or anything here. One of these is concurrency and one of them is throughput. And there's a variety of values of these metrics over time, which is good. It gives us kind of a spread to work with. And the relationship between these two things, how much do you think I can tell from the relationship between these two things? Can I predict the next presidential election? Probably not. But what I can tell is how far is this system going to scale and what is the primary bottleneck? So by doing that, to accomplish that, the first thing that I want to do is just scatterplot. And the axes on this scatterplot are exactly the same as all of the diagrams that we've been looking at for a little while. There's concurrency on the bottom and throughput on the vertical axis. And that is the USL's inputs and outputs. So looking at this, is it linear? Looks pretty linear, right? And one of the things that we could do is we could just fit a line to it and see, holy cow, look at that, 97.8% R squared. How many of you would kill to have a 97.8% R squared, right? There's a lot of data scientists and data engineers in this room where that's like mind-blowingly good fit to a line. But we shouldn't celebrate yet, because what's not shown or what's not really obvious on this chart is that line is not pointing at 0, 0. And that is the first data point in every scalability plot, is that 0, 0 is always an invisible implicit point. So we have to sort of include that. So this may look very, very linear, and usually when people look at charts like this, or when they plot charts like this and say, see, this is linearly scalable, this is kind of the justification for that conclusion. So how bad do you think this is? Anybody want to hazard a guess? Like, is this pretty good, or is this system about to get into deep trouble? Problem. All right, so we have one vote for problem. Do we have any votes for this system can actually scale quite a bit further? I see a couple. Yeah. All right. So let's see how it goes. So to answer, what we should do is use regression, nonlinear regression, and fit the Universal Scalability Law to this set of points. And then let's look at what it looks like. So how many of you want to change your vote? This is actually a highly nonlinear system. Can you believe that? If you look at it, you can kind of see maybe what you didn't see at first, that at the left end, all of our points are a little bit below the line. In the middle, the points are above the line. At the right end, the points are below the line again. That is sort of the seeds of destruction being sown. So this is what this system's scalability really looks like. And this is actually pretty clean. These points I said I didn't show you on the previous slides, the time range that this was taken over. I just took these right out of a time series database. Our time series database at VividCortex, and I think I took it over 5 or 7 days. So each of these points, there's probably like 300 points. Each of these points represents a fairly decent amount of time. You know, it's some amount of minutes, maybe it's 10 minutes or so, averages. So each point, each little circle on here is an average throughput and an average concurrency over whatever, 10 minutes of time. And so the system is actually behaving fairly cleanly and fits very well to the Universal Scalability Law. And one of the reasons for that is, first of all, that the system is well behaved. And the other is that I've taken those averages over sufficiently long periods of time, and that we've got a sufficiently large spread in the data points to really give us some room to fit. So if you look at concurrency, it goes from, what is it, 5 up to 18 or something like that. That's a decent amount of concurrency range in which to fit. So how much headroom does the system have? If you just look at this, you know, how much further do you think this system can scale? Maybe if we had looked at the linear line, we would have thought that maybe we can get twice as much work done from this system or something like that. We look at this and it starts a little bit less exciting. You know, the way that this chart is plotted, there's actually quite a bit of white space on the horizontal axis, and it looks like, oh, we could maybe, you know, like double our concurrency or load on this system. But that's really an optical illusion just of how I've chosen to put the axis range. I could have made that go out to 1,000, and it would be sort of an Edward Tufte faux pas where I'm kind of lying and saying, see, the dotted line can go out to 1,000. But what we really see happening is if you kind of look at where this thing starts to taper off, and you can calculate where it tapers off and so forth and so on. But I'm just doing this with no math. I'm just like drawing some lines on the chart and going, how much headroom is there? And the reality is there's not much. I mean, I don't know, what, 10, 12, 15% of headroom before this system is going to stop really giving us any payback under increased load. And the bad thing about this is that as we get out into the higher load regions here, this system's utilization is going to get very high. Performance is going to go to hell. It's going to get highly variable. It's going to start stalling. You know, wait times are going to, you're going to have outlying latency outliers, and you may even get this system past a threshold where it gets stuck and turns into the spiral of death, and it's the kill-9 territory that, you know, it gets really, really ugly. If we actually push this system to higher concurrency, or if we looked at shorter term time averages that would reveal more of the variability that's kind of averaged away in these points, most likely what we would see is that as the scatter plot goes to the right, it probably starts to look much less neat and doesn't lie along the dashed line very cleanly. It probably turns into more of a hairball kind of thrown on the screen. All right, so we went from, wow, it looks pretty linear, to I'm kind of worried about this system approaching the limits of its capabilities in, you know, a couple of simple moves. All right, so that I think is actually pretty transformative takeaway for capacity planning, where capacity planning used to be just sort of art and napkin math and no real certainty about whether it was actually going to match the real world, or the insanely hard queuing theory analysis and things like that. You know, we've just taken 2 simple measurements from our system, throughput and concurrency, and we figured out how close we are to the ceiling. So let's see how much further we can take this, not presidential elections, but we can do something really interesting from the outside of this system, treating it like a total black box. We can actually peer into it like an X-ray and figure out what's going on inside there, even without knowing anything about the internals of this system. This is fairly easy to do. We can answer the question, what is this system's primary bottleneck? There are 2 kinds of bottlenecks. There is that serialization penalty, where we get nonlinear scalability because of things waiting in line. And there's the crosstalk or coherency penalty, where we get nonlinear scalability because of things making each other do extra work. So these parameters in Universal Scalability Law have a very real physical meaning. This isn't just, you know, picking a parabola and saying, you know, I can fit this curve to the points or something like that. There's a real physical model that this all comes from and a theoretical basis behind it. And and it does work. All right, so I've listed the physical meaning below here. The throughput of single-threadedness, that's the slope of our line. We've got sigma, which is just the fraction of the workload that is serialized, and kappa, the fraction that's crosstalk. And when you regress something, what you're really doing is getting estimates of the parameters. So by regressing against these points, we're getting estimates of how much serialization and crosstalk there is in it. And this system's parameters are plus or minus 7.5% of serialization penalty and a very, very small fraction of crosstalk. Right? There are other systems, if you click through in the references at the ends of these slides, there are lots of other systems where it's totally the reverse. Sort of stereotypically, you might see this in a Node.js system that is single-threaded, and lots of things are waiting on single-threadedness. You might see things that have a lot of crosstalk penalty in very heavily multi-threaded systems that have a lot of overhead of the multi-threadedness. For example, a lot of JVM applications spend a lot of time in thread scheduling and things like that, or in the internal cross-thread communication. And so you can see that really clearly when you do this regression. You know, sometimes it's not, but in this case it is. And this, by the way, this is a MySQL server. This is running in our production systems. And you know, its bottleneck is probably mutexes. Just an internal implementation detail of the database server. But it gets just very nicely kind of teased out, and we separate the wheat from the chaff, and we go, if we want this system to scale better, to give us better performance, the one thing that we should be thinking about is how can we reduce the contention penalty over serialization? And it might be at the operating system level, it might not be the database server, but that would be the kind of thing that I would go look for if I were going to try and make this thing go faster or go further. All right? So who is surprised that you can get that kind of insight from just taking a couple of metrics and doing a regression? I know it kind of blew my mind. And so we are at the end. And that's all I've got for you today. If you want to scan the QR code, you can get these slides. I'll leave that there for you for a moment. But the next slide after this has some references that you can click through to. I wrote a little book about this. You can download that for free from the VividCortex website. There's a link there. And I'm happy to take a couple of questions, and then I should go to the office hours and probably answer the rest of the questions there.
Could you explain the intuition for those coefficients again, where they're coming from?
The intuition for the coefficients. Okay. So the gamma on the top, the little Y-looking thing, is the, if you were to put n equals 1 in here, then everything kind of disappears from the denominator. All of the components disappear from the denominator, and you just get, it reduces to n over 1, or sorry, gamma n over 1. And so gamma is the slope of the line. Gamma is the line that goes from 0, 0 through concurrency of 1, and then, sorry, I guess I'm doing this kind of in a reverse for you, and then goes in a linear line from there. And then the intuition for Amdahl's law is a little bit difficult for me to explain kind of verbally. But the idea is that as, it's easier to explain in a different form of Amdahl's law, but it does, when you rearrange the algebra, it rearranges into this n-1 component on the bottom. And then the intuition for the kappa component is that the possible amount of kappa crosstalk is the n times n-1 number of potential interactions between things doing work concurrently.